The last video we talked about Newton's method for a system of equations, n equations and n unknowns. And the Newton method is a very elegant method, but there is a need for derivatives, and in this case there are a lot of derivatives. If you have a function in 5 variables and in 5 coordinates, there are 25 derivatives. If the user is the one who has to provide them, then he will never use that algorithm, because either he does not remember the rules of the derivatives in that case, or it's just too much work to provide, or there is no term function but a function which can be called by an algorithm or by the user, but there is no term you can derive. So we need definitely an algorithm without derivative. The Newton method was more for didactical purpose. For practical purpose, we need something without derivatives. And in this video, I will show you one possibility to avoid derivatives. This is a very simple idea, and more sophisticated ideas will be used in practice, but yes, this algorithm will also work. So we have n equations and n variables, and we can formulate the equations to be a function, and we are looking for the roots of the function. And if we say Newton works and it's a good method from theoretical point of view, we can imitate or approximate the derivatives. And that's the idea we follow in that video. How can we approximate a derivative for a function in one variable? We can approximate the derivative by this quotient. We evaluate the function at 2 points, and then we divide by the difference of these two arguments. When we talked about derivatives, I told you a better idea to better approximate the derivative, but in our case that would mean more function evaluations, so we work with that simple approach. Okay? And this is the simple approach, and if you try to understand what's going on for a system, what is the partial derivative, then it's obviously clear. The function f consists of 2 coordinates. There's a f1 function and an f2 function, and then the partial derivative of the f1 function. F1 is a function taking 2 input arguments and returning 1 output argument. You can visualize here to be something like a mountain or some landscape with some mountains. Okay, and then what is the partial derivative? Then you are at some point, you want to know the partial derivative with respect of x1, then go a little step to the right in the direction of x1, then take the function value at these 2 points, you get something here, and then the slope of this tangent or this secant is an approximation for the derivative, and that's what's written here. It looks like horrible, but it's not that horrible. How can we write it in a more easy form and being correct, still being correct? I don't know. So I have to write down this horrible looking fraction, but it's not really that hard. There are some arguments untouched, and then there is a block of arguments untouched, and in the middle there is an argument xl plus hl, and this one is touched, and that's the path from here to here. Okay, and then we have an approximation of the Jacobian, and then we can do exactly the same which we did for the Newton method. And what did we do? We solved that system. It's a linear system. We want to find solutions of a nonlinear system. What we know is how to find solutions of a linear system. So we can use the linear system solver to approximately solve the nonlinear system. That's a very crucial thing, and I want to take your view to that point. We know how we do the one thing, and then the other thing we don't know how to do, we approximate by the thing we can do. Okay, what do we have? It's a superlinear convergence as long as the Jacobian is invertible, and the user has to provide a starting point, an initial guess of the solution. That's a very heavy drawback, but this drawback is present in every algorithm of this world. You can't get rid of, only for very special classes, for example polynomial equations, then you can get rid of, but in general you can't get rid of, and that's a really nasty thing, really ugly. Nobody likes that. Everybody's surprised that he has to provide an initial guess, but that's the truth, and please never forget that truth. That's a very crucial thing. Okay, so the disadvantage is the thing I talked about, and then with this initial guess there is only one root which can be found, at most one root, and if there are more than one solution, then you have to provide an appropriate second guess for the second solution, and then the algorithm can find maybe this one. And if you don't know how many solutions there are, then you are in a very bad situation. But that's the truth about every algorithm in this field. That's the code. The code is very similar. It's more or less a copy from the Newton method with slight modifications. You can check which are the modifications. Here is the guess of the Jacobian, and the rest is more or less the same. And then you can call it here in that way. The code is not really optimal, it's suboptimal. The concept of having the user to provide the age vector is not a good idea. In my algorithm you can work with different ages. Okay, and keeping that age for the whole process is not really a good idea. Better would be to adjust, but this is not an algorithm used in practice. It's only for didactical use. You must know the details. I can ask in the exam, but it's not really of practical use, so I don't care too much about things which are not perfectly optimal. If you want to learn about algorithms which are used in practice, then Google, ask ChatGPT, please explain to me Broyden's good method. There's also Broyden's bad method. That's a funny kind of thing. So these are the two algorithms which are mentioned most times and which are used most times. Okay, so far this was the theory. Then let's give one example, and let's work with a very simple example. We have these two equations. What is the first step? It has nothing to do with the Newton method without derivatives. It's always the first step for every algorithm you might use. It's bring it to a is equal to 0 set of equations, and that's very simple because bring the right hand side to the left, and that's all you have to do. The next thing is take that to be a function, and you're looking for the root of the function. Then the user, you, have to provide some initial guess, and let's use 1, 2. Two numbers I did not think too long about. I want to show you an example, so let's take 1, 2, and let's work with h1 is to be 0.1 and h2 is 0.01. What do we need? We need to evaluate the function at the point 1, 2. This is the 1, 2. And if you take 1 to be x and 2 to be y, then you have 1 plus 4 is 5, minus 4 is 1, and minus 5 is this minus 4. And x squared is 1, this cubed is 8, 8 minus 2 is 6, minus 2 is 4. So this is the function evaluation. Then we have to evaluate at 4 points, because in this case 2 variables, 2 equations, 2 times 2 entries in the Jacobian. So here it's that number, then we take the difference of that number and divide it by the h, and then we get minus 1.9, and so we do for the other function, for f2, the second coordinate, so we are here now, and then we get 5.48, in the end 14.8, and then the approximation of the y derivative is that, and for the second coordinate we get that, and so we have the Jacobian taking these 4 numbers and putting them into this matrix, and this is the Jacobian, or the approximation of the Jacobian. Then we have the following linear system. Find the solution of minus function value, and you can use some electronic help in that case, or take the inverse of that matrix, swap these two, take the negative of them, divide 1 divided by the determinant, and multiply from the right hand side and multiply with 4 minus 4, and then you will get the solution, and this is minus 1, more or less minus 1, and plus 1, more or less. And then we can do the step going from our initial guess 1.2, we go a step of that size. Adding these two numbers, you get 0.01 and 3.056. And this is our improved guess for the solution. And then you can iterate that process, take that instead of 1, 2, and do the whole process again. And so you can iterate, but I don't want to do. I think that's enough for the example. Okay, so we are done. That was our derivative-free version of Newton, and that's all what I wanted to say.